Hello everyone, this is Chandrakant Mishra. Today we are going to learn transient analysis of the circuits. Let's begin. So for electrical networks, that is response of a system has two parts, namely transient response and steady state response. So main discussions will be transient response, the response of a system or network to change from equilibrium. That means the system or the network is in the equilibrium, or you can say the steady state, or you can say the inertia, and you are disturbing that system. Then we'll have the transient response. In electrical networks, transient exists due to the energy storing elements. What are the energy storing elements in an electrical networks? That is your inductors and the capacitors. Transient behaviors present for short period of the time immediately after the system is disturbed from the equilibrium. That means it will ultimately transient behavior will die out over the time, but just when the your equilibrium is disturbed, you will experience the lot of transient in the systems. And the properties of the transients are rise time, overshoot, settling time, delay time, peak time. These are the measures of the your transient response. Then is a steady state response. Steady state response is an equilibrium condition, or we can say the inertia conditions. That means whenever any circuit at in one state that continues to be stay in that state, then we call that state is the equilibrium conditions or equilibrium state. In the equilibrium states, the effects of transients are no longer existing or important. That means enough time has been passed after the disturbance or the after the equilibrium has been disturbed, and so that the new equilibrium state has been achieved and all the transients has been died out. So in general, the response of a network can be written as transient response plus steady state response. Transient response, it reduced to zero as t tends to infinity, and mostly it felt when the equilibrium is disturbed. And steady state response, it is the response that remains as t approaches infinity. And later on you will see that the 4 time constant of the networks is the deciding factor to consider whether the system is in transient phase or in the steady state phase. We need not to wait for the infinity time to get into the steady state. What in theoretically it is the we need to wait for a infinite time to get the steady state response of a circuit. But within 4 time constant we can achieve the 98% of the final state values of the system response. So 4 time constant is treated as the steady state response. If 4 time the time constant of the circuit is allowed for the circuit, then we can say the circuit has reached to the steady state value. So consider this circuit. There is a 10 volt voltage source, one resistors, one capacitors. We assume that initially capacitor has zero charge across it. So at t equal to 0, switch is closed. The general response of the output voltage or the voltage across the capacitor is the 10 minus 10 e raised to the power minus t. How it will be calculated, we will learn in these topics. This is the main topics of the discussions. This 10 volt, or you can say the response that V0t equal to 10, we call the steady state response, and the minus 10 e to the power minus t we call the transient response. And when we add together, we have a total response for t greater or equal to 0. For transient response analysis, we use the Laplace transforms or S transform method extensively, and we'll also look into this later on. So we see that a system response is divided into the transient response and steady state response. You might have come across the one response called the frequency response. What is that response? Is simply it is the steady state response of a system to sinusoidal input. When we apply a sinusoidal input, and what will be the steady state response of the circuit is termed as a frequency response, and frequency is varied, okay, from DC to infinity. For this case, we use S equal to j omega in the frequency response of the network, so that all the calculation can be made. We shall now confine our discussion for transient response of the networks. The main topics of the discussions today is the transient response. So before moving into the deep into the transient response, first of all, I want to tell you that the time response or time plays a vital role. Let's say it is your time axis, right? And this is your 0. Normally you will come across the circuit when circuit is closed or equilibrium is disturbed at t equal to 0. But we'll take a general case, let's say t naught. And this is our, we can say, Lakshman Rekha, like that, and before t equal to 0, after t equal to 0. Here the switching action takes place, whether switch is closed, or we can say we have a closed switch and switch is open. See the notation here. So this indicates the switch is closed at t equal to t naught, and this indicates the, let's say, switch S1, and this is your switch S2, and this indicates the switch is open at t naught. Okay, so here in the transient response we'll see that just before switching and just after switching, let's say at t equal to t0, switching action takes place. Switching action takes place. So notations are for just before switching, and just after switching. So just before switching, we designate all the values as t naught plus, that is t0 plus, and just before switching we'll denote it like t0 minus. So our switching action takes place at t equal to t naught, and then just before switching is the t naught minus, and just after switching is the t naught plus. So before moving to the circuit, and these are the essential things you should know about the elements, because we have three type of element: resistors, I mean to say passive element, resistor, inductors and capacitors. So we'll discuss the elements and its initial conditions, and switching here takes place at t equal to t0. See here, equivalent circuit. See, whenever a switching action takes place, whether it is open or closed, the equilibrium is disturbed, and we will see the element as per the given table. We have a resistors. When the switching action is taken place, so just after switching t equal to 0 plus, switching means either you open or close, so that's why in general I say the switching action. So at t0 plus, what it indicates, that is just after switching, resistors remains a resistors, and as t tends to infinity, that is the steady state conditions, exactly R remains R. That is, there is no change in the resistors whether after switching, or you can say the transient state or steady state. So resistor, for resistor, you can have the same response for transient and steady state. Then come to the inductor. Inductor can have two cases. Case A, without any initial current through the inductor, and with an initial current through the inductor. When you don't have any current through the inductor, initial current or initial flux through the inductor, then just after switching it will act as open circuit. It will act an open circuit, and at steady state current will flow and it will act as a short circuit. At steady state it will act as a short circuit. And when some initial current is flowing through inductor and switching action taken place at t equal to 0 plus, then it will act an ideal current source. That is, just after switching action it will act an ideal current source of the value the initial current. Okay, so at steady state current through the inductor depends upon the new circuit condition, because you have already disturbed with the switching action. So the new circuit conditions will decide the current through the inductor. Then come to the capacitors. We have capacitors which is initially uncharged. So just after switching, it will act as a short circuit. And as t tends to infinity, it will be completely charged, whatever the values across it, and it will act as a open circuit. The second case, the capacitors which has some initial charge. So initial voltage will be Q0, that is initial charge upon C. So Q0 upon C, that voltage will appear just after switching. Just after switching, it will act as a voltage source of initial voltage. See the polarity. See the same polarity what was initially. That will act as a voltage source. And as t tends to infinity, it will act as an open circuit. Voltage across it depends upon the circuit conditions. What we will see here, two fundamental things. Current through an ideal inductor. See, whenever I say here resistors, capacitors, inductors, I mean inherently these are all ideal elements. So I need not to again repeat the ideal things. Okay, so I inherently mean that I assume that all the elements are ideal in this case. So current through an inductors does not change instantaneously. Suddenly you cannot change the current through an inductor. Okay, and second case is the voltage across capacitors cannot be changed instantaneously. Whatever the voltage before switching, that will remain after switching for t is equal to 0 plus for short duration. I mean say instantaneously. That means whatever the current at t0 minus, the current will be same. Suppose it is a inductors, some current is flowing. Okay, an inductor, some current is flowing through the inductor, let's say 1 ampere, and switching action takes place at somewhere in the circuit. That currents will be same also at t equal to 0 plus. That is, you cannot change the current through an inductor instantaneously. Same way, voltage across the capacitor cannot be changed instantaneously or does not change instantaneously. But there are two special cases you need to give mind to it. it can be changed instantaneously in cases when the current reaches the infinity. For this case, you see, if you want to change the voltage across the capacitor instantaneously, then you need an infinity current of small duration. In other words, an impulse current of required magnitude, so that before switching all the capacitor has a 0 volt. Look at the circuit. When you switching takes place, all the capacitors have charged instantaneously due to a short pulse. You can say short impulse current pulse. You can say impulse current, so that your charge across all the across the capacitors will be finite, because you know that del t dt 0 minus to 0 plus is the 1. Okay, 1. So if I make this charge, because charge will be finite, you cannot have infinity charge across the capacitors. So to meet this current should be, if you charge your finite, this current should be an, let's say, a del t like term, so that the total charge will be the area across these del functions. So dual case also exists. You can have dual situation. I have told you that current through an inductor cannot change instantaneously, but it can change instantaneously if the voltage is an impulse pulse. So in this case, you see that when you directly connect the current source to point B, all inductors will be current will be flowing, because this is a current, pure ideal current source has to be divided. For that, your flux linkage, okay, your flux linkage will be the V dt t0 minus to 0 plus. So there will be finite flux linkage, and to achieve this, your V should be a function of impulse, so that you can have a finite flux linkage. Okay, so in summary, we see that to change the current through an inductor, an infinity voltage of short duration is required. You can say that impulse voltage is required. Same way, to change the voltage across the capacitor instantaneously, and impulse current is required. These are the two special cases, except all the gate question will be concentrated on the general case, unless you come across the some special case where you need to remember what I have told you. Need not to go with all the general response. Let us go understand the transient response through example. Okay, that will be clarify more details. For the circuit shown below, find I1. See, this is the circuit. Okay, it is in the uncharged conditions with switch open, and at t equal to 0, switch is closed. Find I1 0 minus, I2 0 minus, IC 0 minus. What are the I1? Here is the I1, I2, IC, and then VC 0 minus, that is voltage across capacitor before switching. Similarly, we need to calculate just after switching. Also, we need to all this quantity just after switching, and all this quantity steady state. I mean to say t tends to infinity. So one by one we will consider. So here I1 0 minus, I2 0 minus, I2 0 minus, IC 0 minus, and VC 0 minus. So you can say that just before switching, circuit was in the dead condition or relaxed conditions or on charge conditions. So there will be all the currents and voltage across the capacitors will be 0. Now I close the switch. So this is the when it was in the open conditions, this is an equilibrium condition. So when I close the switch, we have studied when the voltage across the capacitors cannot be changed instantaneously. So see we need to replace the T0 plus element, or you can say the equivalent circuit. So resistors remain resistors, these resistors remain resistors, and just before switching capacitor voltage was 0. So after switching it will act as a short circuit. We have just now covered. So now you just do a circuit analysis and you will find, as you know that this terminal node A and node B, after switching it is short. So we can easily say that voltage across a short is 0. So VC 0 plus is your 0. As A and B are in the same potential, so no current flows through the 10 ohm resistor here. So the I2 is 0 plus is 0. See the notation, I2 0 plus. And the current I1 will be your I1 0 plus is your 10 upon 10, which is 1 ampere. And same I1, so IC, because no current flow through this 10 ohm resistor, so I2 0, so IC equal to I1, which is 1 ampere. So this is not the final value, you can say that just after switching. Now come to the third case, as t tends to or t equal to infinite. At t equal to infinity, switched circuit achieves the equilibrium. I mean to say the capacitor will be completely charged. So equivalent circuit, you can see the capacitor will act as open circuit and the resistors remain resistors. Now you can analyze the circuit. So I1, no current flows through the capacitors as the capacitor has been charged fully. So the current I1 equal to 10 upon 10 up plus 10, that is the 0.5 ampere. I1 equal to I2. And IC because it's open, so IC will be the 0 ampere. And what about the VC, that is how much voltage the capacitors has been charged. This is the same as the voltage across this 10 ohm resistors. So that voltage will be the, just apply a simple potential division, 10 upon 10 plus 10 into 10, which is 5 volt. Okay, moving to the next example. So here we have an inductors and a switch and 2 ohm resistor, 3 ohm resistors. At t equal to 0, switch is closed, and before that it is in the steady state, we can say in the uncharged condition or dead conditions. So t0 minus, all the values will be 0 because it is in the uncharged conditions. At t equal to 0 plus, so as I told you, there is no current through the inductor, so it will act as an open circuit at t0 plus. It has to maintain its property, that is the current through an inductor cannot be changed instantaneously. How to represent this current? So that current will be represented, whatever the initial current is 0, so how to at t equal to 0 plus, how I will represent this current? With an open circuit, obviously. In that case only I2 will be 0. So open circuit, that's why I have also discussed in the table at t0 plus, the current, if there is no current through the inductors, it will act as a open circuit. So you can now easily calculate I1, I2, all these things. So your I2, because it is open, so 0 ampere, I2 0 plus, that is just after switching. And I1 0 plus, and this is I1, okay, I0 plus and I1 0 plus, same current will flow 10 upon 2 plus 3, that is the 2 ampere. And V0 plus, that is the output voltage when 0 plus, so it is open, so that voltage is same as the voltage across the 3 ohm resistors. So 3 apply a potential division here. 3 upon 2 plus 3 into 10, which is 6 volt. So now let us move to the t equal to infinity. As I have already told, a t infinity inductor will act as a short circuit and the current will be decided according to the circuit conditions. So I1, as you know that at t infinity, this portion is the same, that is the node A, node B at the same potential. No current flows through the 3 ohm resistors. So I1 will be obviously 0, and I equal to I2, which is 10 upon 2, which is equal to 5 ampere, and the voltage V0, because it is a short, so obviously V0 equal to 0 volt. Okay, learning all these initial conditions and finding the values at a specific point, like just after switching and steady state condition. Let us move to another important calculations, that is initial. We just now calculate the initial values. Let us investigate or calculate the initial, finding initial rate of change of response. Initial rate of change of response, that is how, in what rate it is changing initially, that is di upon dt, dv upon dt, d square I upon dt square, all calculated just after switching. The procedure is very simple. Okay, the procedure is very simple. We'll go through with an example. Let us consider this circuit below. Capacitor C has initial voltage of 10 volt. The capacitor C has, this capacitor and resistors, it has initial voltage of 10 volt, and this is before switching. At t equal to 0, switch S is closed. Find I0 plus di upon dt 0 plus d square I upon dt square 0 plus. The process is same. First you calculate the 0 plus values, then write, after closing the switch, write your dynamic equation involving the elements, and then evaluate at 0 plus. So before moving, I need to write all the dynamic equation for resistors. The equation V equal to IR and I equal to V by R. For capacitors, V equal to 1 upon C integration of I dt, and I equal to C dV upon dt. So nomenclature is like this, that is the convention is like this. This is R. In circuit theory, convention is very much essential. C, and this is your current flowing into the positive terminal I, and this is your V. And same way inductor, so V, and this is your current I, and this is your L. So for inductor, we have, for inductors, your V will be the L di upon dt, and I will be the 1 upon L integration of V dt. These are the all the dynamic equation of the circuit elements you need to know. So let us move to the finding the initial conditions. So first of all, as usual, we are doing at t0 plus, capacitor will act as a voltage source. The current I will be the 10 upon 2, that is 5 milliampere. 10 upon 2 kilo 5 milliamperes. Writing differential equation for the circuit with the KVL. So see here, I'll write the KVL around this circuit. So just write the KVL, Ri plus 1 upon C integration of I dt. Then I'll differentiate to have a differential equation. So R di upon dt plus 1 upon C I. So DIT, now see here, DIT upon equal DI upon dt equal to minus I upon RC. Now put the values here. So now you have di upon dt 0 plus is equal to minus I0 plus upon RC. I0 plus already we have calculated, 5 into 10 to the power minus 3. Put the value of R and then C, and you will have the 5 upon 20, which is minus 0.25 ampere per second. Suppose you want to find a second derivative, then again differentiate it. Okay, differentiate it, you have already calculated. So simple process is involved to get the result. Now discuss the how to find the response for all time. Before we have calculated the time at t equal to 0 plus, that is just after switching, and at t when t tends to infinity, that is the steady state value. But we have not touched yet the what will be the response for all time from t0 plus to infinity. So this involves a lot of process. I mean to say, you need to find the initial conditions first, then final conditions, then write the differential equations, then you have to solve the differential equations, then find the arbitrary constant, then you will find your solutions. This is laid down process. But you can, another way is to go through the Laplace transform, convert all the elements in the circuit into the Laplace transform, then you solve the circuit, voltage or current, whatever you want to solve, then it will be in a algebraic expressions, then you partial fraction the algebraic expressions according to the Laplace transform pair table, then look up the Laplace transform pair table to fix the time domain response. This is another way. So which one we will consider? We will consider the both the one, and the time domain analysis, also Laplace domain analysis. You need to decide in which way it is easier, or you can say the easy to get at the result. So let us consider this circuit. We will solve this question. For the all time, we need to find the VCT for t greater or equal to 0. That is for all time. So you know, so that you see here the switch was at the position B for long time, and at t equal to 0 the switch is moved from the position B to A. So as it was in the position B, I can say the initial voltage VC 0 minus equal to 0 volt, that is capacitors was uncharged earlier, and same will prevails for the VC 0 plus. Now your circuit looks like this. When I move to the position A, R and C, and this is your VC. So write the KCL here. This is your VC. So this current is this current. So 10 minus VC upon R is equal to C, the current through the capacitors. So C dVC upon dt. So you have dVC upon dt plus VC upon RC equal to 10 upon RC. So what is the RC? RC was the, R was your 2 kilo ohm and C was the 100 microfarad, that is 200 into 10 to the power minus 3 second, that is 0.2 second. Okay, so we have dvc upon dt plus 1 upon 0.2 is your 5 vc equal to 5 into 10, which is your 50. So you can see this is a first order linear constant coefficient differential equations. So I'll only consider there is a lot many ways to solve, but I will consider the general way, that is find the complementary functions and particular integral. So complementary functions, we'll consider this homogeneous equation dvc upon dt plus 5vc equal to 0. So s plus 5 equal to 0. So s equal to minus 5. So complementary functions will be the c e to the power minus 5t. Then we'll move to the particular integral. So your pi is the 50 e raised to the power minus 0t upon s plus 5 evaluated at s equal to 0. So 50 upon 5 equal to 10. So now we have VCT. VCT is equal to complementary functions plus particular integral. So complementary functions was your c e to the power minus 5t and the particular integral is your 10. This is the general response. We need to find the arbitrary constant c. So for that we need to look for the initial values of VCT. You check the circuit here, the initial values. So VC0 minus equal to VC0 plus equal to 0. So initial value evaluated is the 0. So 0 is equal to e to the power 0 is 0. Sorry, e to the power 0 is 1. C plus 10, which gives you C equal to minus 10. So put these values. So you have VCT is equal to minus 10 e to the power minus 5t plus 10. So you have 10 into 1 minus e to the power minus 5t for t greater or equal to 0. You can check your result whether it is correct or not. At t equal to 0, e to the power minus 0 is 1. So 1 minus 1 is the 0. So we see t. So we see t equal to 0 plus or 0 equal to 0. Now check for the t equal to infinity. So e to the power minus infinity is 0. So 1 minus 0, 1. So 10. And from the circuit you can also check when the switch is at position A for long time as t tends to infinity, ultimately capacitors will be charged fully. So 10 volt will appear. So this is the process. But if you have a constant voltage like battery and a single time constant like a combination of you can say single R or combination of R and single time storage energy storage single energy storage element or parallel or series combination of energy storage element altogether, then a single, I mean to say a single time constant circuit, you can fix a relations which will helpful in solving the question in the GATE or engineering service exam. This is the relations. See, the preconditions are input is constant, that is a step input like a battery connected and you have a switch and switch closed or open. Time constant must be single, that is when only single energy storing elements involves. Following relation greatly simplifies the procedure for finding the response when the equilibrium is disturbed. So in general I'll write xt, it can be voltage or current xt. So first is the x infinity, That means the values of x as t tends to infinity minus values of x as x tends to infinity minus x 0 plus just after switching e raised to the power minus t upon tau. E raised to the power minus t upon tau, very important relation you should remember, because you will see the lot of questions will be appearing with, and you can fix it, these relations. Okay, a time constant of the circuit, tau is the single time constant, so tau is the time constant of a circuit. Time constant of a circuit, if inductor is involved, so you need to find Leq upon Req, that give you the tau. If capacitor and resistor, so Ceq Req, that is equivalent capacitance into equivalent resistance. So first of all, how to find the time constant? Just see here. I'll go through the example. It will be very clear. So this is your inductor. Just look from the inductor and sort the any sources involved according to the source reduction rules. Like if it is a ideal voltage source, reduce it to 0 or short circuit, and ideal current source, reduce it to 0 by making a open circuit. So when you reduce to 0, the inductor only sees the R. So here the time constant is L upon R. What about this? Same way, reduce this to 0. So capacitor see only R. So time constant will be the RC. And you see here, reduce the source to 0. Capacitor sees like this. So R equivalent will be the R1 plus R2 parallel R3. Okay, and the C R equivalent, this is your R equivalent, so C R equivalent is your time constant. Same way you see here, capacitor sees the R1, that is the R2 plus R1 parallel R2. This is R equivalent into C for the time constant. Okay. For this case, this inductor, when you sort it, so R1 parallel R2 plus R3. Same way this case, sort it, R1 parallel R2 parallel R3 is the R equivalent, and C equivalent is your C1 parallel C2, because it is a series connection. So this will be C1 parallel C2, I mean to say C1 C2 upon C1 plus C2. You can check all these things. Okay, this way. Let us move to the example we just now did it here. So how simply we can do it, you see here. Find the first, let me change the color. So VC 0 plus, already we have calculated, that is 0. VC infinity, that is capacitor charged fully, 10 volt. Tau is, you can see that it is connected here at the A. So reduce the voltage to 0. The capacitor sees only R. So R equivalent is the R and C equivalent is the C. So R is the 2 kilo, 2 into 10 to the power 3, and your C is the 100, that is 0.1 into 10 to the power minus 3. Okay, so you have 0.2 second, right? Now fix it. So your VCT is equal to VC infinity minus VC infinity minus VC 0 plus e to the power minus t upon tau. So VC infinity is the 10 minus 0 e to the power minus t upon 0.2. So ultimately the result will be the 10 minus 10 e to the power minus 5t. As usual, see the how much time it took to find the result with following the procedure. But if you know the two conditions, a single time constant and a step voltage or battery voltage with a switch, then you can easily fix it. Remember that. It should not be a exponential functions, it should not be a sine functions, but a step functions. Battery and switch will give you a step functions. Let us move to the GATE questions which appeared in the GATE 2000. The switch in the circuit in the figure is in position P for a long time. At this point was in the equilibrium at the point P, and then move to position Q at the t equal to 0. At t equal to 0, it is moved to the Q. You need to find the value of initial rate of change. We have calculated. The procedure is find the initial values of the all the quantities, then find the put the differential equation with the KVL KCL, then calculate the values at t equal to 0 plus. As you know that before switching we need to find the t0 minus. So the circuit would have been like this. Is the 5 kilo, I mean to say t0 minus, then here 5 kilo, 10 kilo, inductor would have been a short, and capacitor will be acting as a open. So this is your VC, this is your IL, and obviously it will be connected, right? I am calculating the t0 minus. You can easily see that this is the 20 kilo. Okay, it has nothing to do here. This voltage 20 volt appear across this. So IL 0 minus is equal to 20 upon 5 plus 5 plus 10, which is your 1 milliampere, because all these are in the kilo, and VC 0 minus will be the voltage across this 10 kilo. So 10 upon 5 plus 5 plus 10, that is 20, into 20, that is 10 volt. As I have told, this is not the special case because we have a resistor through the inductor, also capacitor is connected through the resistors. So voltage across the capacitors cannot be changed instantaneously, and voltage current through the inductors cannot be changed instantaneously. So I can safely write IL 0 plus equal to 1 milliampere and VC 0 plus is equal to 10 volt. Okay, now come to the, let us assume that switching taken place. So write down the equation for the switching taken place. 5 kilo, switch closed. Here is your capacitors C, and here is your 10 kilo. Here is your inductor. We need to find, this is your VC. So let's say this current, this is the current, this is the current. Let's say this is your I1, this is your I2, this is your I3. According to the KCL, I1 plus I2 plus I3 equal to 0. So which implies, what is the I1? I1 is the VC upon 5 kilo. Then I2 is the C dVC upon dt. What is the I3? I3 is the same as the IL, na? That is your IL equal to 0. So we have dVC upon dt C is equal to minus IL minus Vc upon 5 kilo. So C dVc 0 plus upon dt is equal to minus IL 0 plus minus Vc 0 plus upon 5k. So we have already calculated my IL 0 plus, that is your minus 1 milliampere, and then Vc 0 plus is the 10 upon 5 milliampere. So you have the minus 3 milliampere. So dVc upon dt 0 plus is equal to minus 3 milliampere upon C, which is minus 3 upon, what is the C? C is your 1 millifarad. So milli cancel. So you have minus 3. C is a dVc upon dt. So volt per second. So this is a 2-mark question. So how easily we could do this here? By following the correct procedure. So this is your option C. Let us move to the next questions, which is again has come from the appeared in the GATE 2021. Same concept, but little bit extra. In the circuit shown in the figure, the switch is closed at time t equal to 0, while the capacitor is initially charged to minus 5 volt. That is Vc0 plus is equal to minus 5 volt. Here is the Vc0 plus. The time after which the voltage across the capacitors becomes 0, rounded up to 3 decimal place each. So whenever you see a dependent source in a transient circuit, just locate the point where you can Theveninize the circuit. So you can easily see that capacitor as the right end and switch also at the right end, A and let's denote and A and B. So I'll open this and Theveninize the left hand of the circuit. When I Theveninize, I need to find, I got here, okay. So I find the Thevenin voltage. To find the Thevenin voltage, so this will be your Thevenin voltage here. Let's say VTH. So because I have already got here, okay. So no current flows through the here. So here grounded. So whatever the current here, then current will be go there. Current will be go there. So KCL at this node. So this node voltage your VTH. So 5 minus VTH upon 250 ohm equal to VR upon 500 plus VTH upon 250. Okay. But what is the VR? Your VR, you can clearly see that this VR is equal to 5 minus VTH. Clear? So put these values. So 5 minus VTH upon 250 equal to what VR is also 5 minus VTH upon 500 equal to VTH upon 250. You can easily see that this is the 5 minus VTH, 5 minus VTH. So 5 minus VTH take common, 1 upon 250 minus 1 upon 500 equal to VTH upon 250. So 5 minus VTH equal to 500 upon 1 equal to VTH upon 250. So cancel. So here we'll have 2. So 5. Okay. So 5 minus VTH is equal to 2 VTH. So VTH is equal to 5 upon 3. This is your Thevenin voltage. Next step is to find the Thevenin resistance. Okay. So for Thevenin resistance, as usual, sort the reduce the voltage source and current source to 0, and dependent source as it is you have to left. So 250, this will be short, dependent source will be there. Okay, then you have 250 ohm. Then I connect a voltage source here, external voltage source V2, and I'll measure the I2. So V2 upon I2 will give the Thevenin resistance. So let's say marked it, okay, plus minus VR, and this is your VR upon 500, right? VR upon 500, this is your 250 ohm. But see here, if I calculate V2 upon I2, that will be complicated. But what will do, see, I'll use my intuition. So I smartly do like this. Let's say this is my I. Okay, I'll find the V2 upon I2. So V2 upon I, that will give an resistance. So I will have the equivalent resistance will be the 250 and that resistance. I'll do this analysis. This I2, this I is equal to, you see here, same voltage prevails up to here. So this current, that is your V2 upon 250, and this current plus VR upon 500. But I need V2, but you see the V2 and VR relations, V2 equal to minus VR. So put these values. So V2 upon 250, and in place of VR, so minus V2 upon 500. So I will have 500 upon 2 minus 1 V2. So V2 upon I is the 500 ohm. So I got the 500, and already I have another 250. So situation is like this now. This is your 500, this is your 250. Same thing. So equivalent resistance or Thevenin resistance will be the 500 parallel 250. So 500 into 250 upon 500 plus 250, which is 750. So 250 into 750, that is 500 upon 3. Now we have Thevenin voltage and Thevenin I mean to say Thevenin voltage and Thevenin resistance, and we'll at the point AB. Now I connect the switch and capacitors, okay, as it was before. So my circuit will be like this, plus minus, which is 5 upon 3, then Thevenin resistance, which is 500 upon 3. Then I'll connect here that is my switch, then my capacitors of 0.6 microfarad, and see the orientation for the voltage, yeah, VCT. And this is your point B. We have already Thevenized. So this is my switch S at T equal to 0, switch closed. Another thing they have been given, VC0 minus, initial voltage was the minus 5 volt. We need to find the time at which the voltage across the capacitor is 0 volt. When the switch is closed, the capacitors get charged in the opposite directions. So we need not to worry about. Now you see that this is a constant voltage here, 5 upon 3 volt. Switch, there was a switch and single time constant. Single time constant. We know what to apply here. That is VCT equal to VC infinity minus bracket VC infinity minus VC0 into e to the power minus t by tau. Let's tau single time constant, R equivalent, C equivalent. R equivalent is the 500 upon 3, C equivalent is the 0.6 into 10 to the power minus 6, that is 0.1 into 10 to the power minus 3. Okay, 0.1 into 10 to the power minus 3, or I can write it 10 to the power minus 4 second. One part is over. Then VC0 minus equal to, sorry, 0 plus is equal to VC0 minus. Voltage across the capacitors cannot be changed instantaneously, so minus 5 volt. And VC infinity, that is when the switch is closed for very long time, ultimately this voltage will be completely, capacitor will be charged up to maximum voltage in the forcing function, that is your DC value of 5 upon 3 volt. Now apply your relation you have learned. So VC t at any time t, VC infinity, that is 5 upon 3 minus bracket VC infinity 5 upon 3 minus VC0 plus minus minus plus, that is 5 e to the power minus t upon 10 to the power minus 4. So 5 upon 3 minus 20 upon 3 e to the power minus 10 to the power 4t. Still question is not yet over. It says that at what time the voltage across the capacitor will be 0. At this point, one word of caution. Let's check whether our calculation is correct or not. When t equal to 0, there is 1, so 5 by 3 minus 20 by 3, that is minus 15 upon 3, that's minus 5 volt, is correct. And t equal to infinity, when t tends to infinity, 5 by 3, our solution for VCT is absolutely correct. So let's say t at sometime, let's say at t equal to t1, that is my VCT equal to 0. So equate it, 0 equal to 5 upon 3 minus 20 upon 3 e to the power minus 10 to the power 4 t1, which implies e to the power minus 10 to the power 4 t1 is equal to your 5 upon 20, that is 1 upon 4. So take the logarithm of the both the side, natural logarithm, that is ln, that is log base e. When you take this, so we have 10 to the power minus 10 to the power 4 t1 is equal to ln 1 upon 4. When I reverse it, so 10 to the power 4 t1 is equal to ln 4. The ln, your ln 4 is your 1.38386. So t1 is equal to 0.1386 millisecond. 0.1386 0.1386. See here, the time after which the voltage across the capacitors becomes 0 rounded up to the 3 decimal places is millisecond. This is the very important. If they had been asked in the second, you need to add leading zeros in the before this in decimal places. Because it has asked the millisecond, so you need to convert the millisecond and enter the values here. So see, it looks initially difficult, but with procedural you can easily find out the solutions. Hopefully you understand the concept, and see you in the next class. Thank you for watching my video.